Hello. So tomorrow, now I'm recording this on February 27th, Monday, and as of now, the weather forecast says tomorrow we'll have 5 to 10 inches of snow, maybe the worst snowstorm this season. But I spent too much, I wasted too much, like kind of class cancellations so far. But maybe, but I think I need to cancel tomorrow's class. So I am recording this video to make up for the class tomorrow, February 28th. Okay. So last time, let me like, and I don't like to use I don't like online video because actually recording online videos require much more time and like to be equally efficient as a lecture in classroom. So in the classroom, I can do more interactions and like I can write down and I can explain as I write down. But here online I am more limited. I cannot be more proactive unless I spent a lot of time to prepare for animation in the slides or like more interactive slides, things like that. But given the time limit, that's difficult. So let me what I my plan is now. I am going to review what we have done, and also we'll do like will I will show you what I could not show you in the last class, which is one of the tables in the textbook. And then maybe I need to record more makeup videos, but that's coming later. Okay. So okay, let's go. Let me start. First, we started. By the way, the review of the previous materials is an important part of your learning. So repetition is, I believe, repetition is the best way to learn something. Like because maybe I believe your brain feels more comfortable with the repeated concepts. So so that's why I keep repeating the the materials and just to let you see the big picture. Okay. Okay. We started from the potential outcome framework. Um, so formally state the potential outcome framework. We first consider a binary treatment, which is denoted by D. Capital letter D is the decision. We may think it as decision. So it takes either 1 or 0. Treated group and control group, right? So you can divide sample into treatment group and control group. Examples include, in the class, I have used the example of college degree, the effect of college degree on wage, or the effect of hospitalization on your health, or you can think of many examples like the effect of vaccination on infection, for example, or the effect of job training program on the time to find another job. Like we learned many examples of causal inference, and usually or another example was the effect of small class size on test scores, effect of having an aid teacher on test scores. Those are examples you can think of as a treatment. And given the treatments, we think of two latent potential outcomes, y1i and y0i. So everyone has two-dimensional potential outcomes. If you imagine video games, I think it's pretty natural. In video games, like so for example, a player or a character has, speed, power, and many different like attributes, and like that, I have my own attributes, like my potential wage if I do not attend college, my potential wage if I attend college, something like that. However, we do not observe all of those latent potential outcomes, but the realized and the observed outcome for individual I is given by either one of them. It's like switching. So if you choose 1, then the realization is y1. But if you choose 0, then your realization is y0. That is the potential outcome framework. Based on the potential outcome framework, and we assume there are additional covariates or control variables. So you may call this covariates or control variables xi for individual I. And then in this setup, we would like to estimate the average treatment effect, like simply ATE. And in many cases, we are specifically interested in average treatment effect for people with some specific characteristics, like the effect of hospitalization on health outcome for those who are 70 years old, for example, right? So then it's clear. Y1 is the potential outcome if you are treated, and Y0 is the potential outcome if you are not treated. So their difference is the effect of your treatment, the difference like on and off, between on and off treatment. And then you are conditioning on specific characteristics like age or like education or whatever, given certain information, and you take expected value. So expected value, which is average of the difference between potential outcomes for those who have X, right? Alternatively, you may think of average treatment effect on the treated. So now the only difference is you are additionally conditioning on d equals to 1. So I am interested only in the effect of hospitalization for those who were actually hospitalized, right? For those who are not hospitalized are healthy, so we don't need to worry about the effect of hospitalization to them. But we are worried more about the effect of hospital on those who are actually in hospital. Okay, so that's an example. But again, the important thing you need to understand is, again, the potential outcomes are latent. They are not observed. Y1, Y0 are not observable. You cannot calculate them. You cannot calculate this expectation at all. It's average, but these variables are not in your data, right? What you have to do is you have to study the connection between these potential outcomes to the realized outcome. And then to do that, to connect the potential outcomes to the realized outcome, what you need is an independence assumption. Especially, conditional independence assumption is more realistic independence assumption. This means that potential outcomes are statistically independent of the treatment decision, D, but conditional on X. I have explained the idea of conditional independence using like ice cream and ski in the class. So there can be different channels that generate the correlation between these outcomes and the treatment decision. But if you can observe those channels, and include them in your analysis, actually those channels are controlled. So that's how we assume independence. And under this assumption, the average treatment effect you wanted can be calculated this way. So this y is observed outcome, x is observed, d is observed. So exactly, you can calculate them. This is pretty straightforward to calculate that. And simply speaking, this part is the average of observed outcome with characteristic x in the treatment group, and the same in the control group, right? So comparing treatment group and the control group given the same characteristics, okay? Again, it does not depend on latent variables, so this is what you can calculate. So, and in other words, the conditional independence assumption guarantees that there is no selection bias as long as you condition on x. As long as you control for x, no selection bias. Then, okay, that's nice. Theoretically, that's pretty clean and nice. But in practice, what are the variables x? Simply speaking, I recommend you to think of this function. Like those variables, the control variables are typically the variables that affect the treatment decision. These variables are the variables. These are the variables that affect your treatment decision. For example, in class, I considered if the treatment is a college degree, whether you attend college or not, then you can think about a lot of variables that affect your college decision, right? Your family income, your high school GPA, or the expected wage without college degree, a lot of things like that, living expense for college, something like that. And those variables are nice candidates for x. And what we want is we want to express the decision in this way. So the decision depends on variables x and u. So x are observed variables like family income. This is college decision, college entrance, and family income. And u is unobserved, but it should be completely random. We hope this unobserved part in your decision making is completely random. Like it's just like random matter, luck, pure luck, something like that. In this case, we call this as selection on observables. And then the CIA holds. Conditional independence assumption holds in this case. So that's how we understand the conditioning variables. Still, okay, it's so including conditioning variables. Okay, now we learned we need to include control variables, and what are those control variables? Then the next question is how can we control the variable? Simple answer is the most practical answer is to use a regression model. All right, condition on x is actually it's theoretically straightforward, but in practice it can be complicated, right? We learned that in studying saturated models. Okay, so we simplify a saturated model to this simple linear regression, right? We are interested in the effect of treatment on outcome. So rho is the coefficient of our interest. But we to ensure the conditional independence assumption, we have to include x as well, right? X can be multiple variables. It's not that difficult in linear regression. So inclusion of x will help the uncorrelated will make the treatment variable uncorrelated with the error term. That's the conditional independence assumption we need. Those are uncorrelated if you control for x. And then if the CIA assumption holds, then you may interpret rho as the causal effect of d on y. That is our approach. So that's a brief review up to chapter like 3.2.1, right? 3.2.1 is based on this idea. Okay, and then the next step is to study what happens if you do not include x, and then your estimator can be misleading. We will study that behavior, and also we will study what happens if your x is not an appropriate control variable, a bad control. Then you will have another problem of bad control. So I will discuss that in another video. Okay. And thank you for watching. I will come back in another video.